Our next talk will be about Botong Wang, the Singer-Hopf conjecture on certain compact Kähler manifolds.
Thank the organizers for the invitation, especially first time coming to Florida to give talk, and I can be in the 25 Celsius weather instead of -25. It's really good. Okay, so in this talk I will be talking about some topological consequences from non-being host theory and maybe more specifically related to the proof of the Shafarevich conjecture. So the topological conjecture, Singer-Hopf conjecture. Okay, let me write down the conjecture. There are actually many versions of the Singer-Hopf conjecture, and I will write a few of them. Let's say M D is a compact linear manifold. So 2D means the real dimension is 2D. So suppose M is a manifold satisfying. The condition that M has non-positive sectional curvature. Or I could also assume that M is a spherical, which means that it's a classifying space, or the universal cover of M is contractible. Can I read my writing now? If it's guys too light, please. Then the conjecture, the Singer-Hopf conjecture says that first the Euler characteristic of M is like by this property. In other words, the sign of the Euler characteristic is determined by the dimension, by or half of the dimension. And another consequence the Singer-Hopf conjecture predict is the alphabetic numbers all vanish except in the middle degree. Okay, so the assumption is 1 or 2 and the conclusion is 3 and 4. But you probably notice that 1 implies 2 by the Cartan-Hartmann theorem. And also by Artia's index theorem, 4 implies 3. Okay, I will not write down that.
Is it the Betty number, L2 Betty of the universal cover?
Yeah, it should be the universal cover. Okay, thanks. And I want to mention that there are many different versions. For example, we could change first we could change the non-positive to strictly positive. Then we would expect a strictly inequality. Yes, I changed to negative. And also I could change the non-positive to non-negative. In that case, I will get rid of this. So the sign will always be in modular with it. And also I'm assuming M is even dimensional. If M is all dimensional, 3 is saying nothing, but 4 is trivial. So in all dimension, basically the conjecture says all the algebraic numbers should be 0. And even further, so later I'm gonna assume M is a compact Kähler manifold. So when M has complex structures, in fact, there are some kind of analog. I mean, this will not be the original Singer-Hopf conjecture, but there will be some analog related to coherent version of this kind of conjectures, which is kind of related to what Philip mentioned in his talk, because he was using mixed order modules, and that really has some coherent consequences. Okay, but for us today, we will kind of focus on this one, and actually later I'm gonna focus on 2, and I'm gonna focus on 3. And in the real case, these are really some very hard conjectures. And in low dimension, maybe dimension 3, 4, there's some, I think dimension 4, 1 implies 3 is essentially Gauss-Bonnet theorem. And maybe in dimension 3 and 4, real dimension 3 and 4, there are some results, but in higher dimension, these are wide open. But once we put some compact structure or a Kähler structure, one can, I mean, put hands on it better and have some results. Okay. So this is work first by Gromov, and then Gromov did the strictly positive case, and then independently by Cao, Beer, and Jos Zuo. They prove that if X is Kähler, then Y implies using some L2 vanishing theorem, which again is closely related to Philip's talk, but this is not the approach I'm gonna focus on today. So today, the goal of today is to discuss something like, so I really want to start with 2. And the whole point is, so 2 is something purely topological. 1 is a geometric. At least once you have some curvature condition, you can expect at least you can do some geometric like calculation. But if you only have a spherical, this is quite challenging. You just its condition is quite tricky to use. So we want to start with 2, and we want to. I mean, definitely we can't just prove the conjecture directly. We have to assume some additional topological properties or assumptions or conditions, and then we want to imply 3. And the approach we take is kind of a different nature from at least this kind of L2 calculation. And for our approach, we can actually prove something, or the thing we prove will be somewhat stronger. But it turns out that if you can prove something like this, we expect the same approach will like automatically lead to something stronger using the approach we are going to talk about today. So instead of a spherical, so we are going to replace a spherical condition by a large fundamental. I think it's a well-known result that if a Kähler manifold is a spherical, then it is has large group. It has large group. So what it means is, or the way I think about it is, I mean, the definition of large group it says any positive dimensional subvariety from group map to from group of X has infinite image. But it's better to think of it this way: is the universal cover of X has no positive dimensional. compact subvariety. It's equivalent to the usual Larmor group. And so why a spherical imply this? So if it's a spherical, then Newton's cover is contractible. If it does contain some positive dimensional compact subvariety, that compact subvariety will represent an non-trivial cycle in okay. So here so I use M when I talk about real manifold, and I use X when I talk about Kähler manifold. If it contains a positive dimensional subvariety, then the subvariety of the image X will represent a non-trivial cycle. But if the universal cover is contractible, we know that anything, there is no non-trivial cycle, topological cycle. So I think that's kind of clear. And then I'm going to replace the condition 3 again by something stronger. I want to say, instead of proving the characteristic of X has some sign property, I want to say the characteristic of any perverse sheaf on X is negative. Any perverse sheaf. This does make the statement at least stronger, right? Because I can take C of X, the constant sheaf of X, and sheaf by dimension of X, which for the remaining part of the talk will be D. So this is the perverse sheaf. So the characteristic of X, Dx, D is actually -1. So it's constant shift by degree D. A shift will change the order characteristic up to psi. And then I will put constant shift as just the order characteristic of X. You see, from this point of view, like this -1 to the D power is actually like it shouldn't be there because you are not thinking about the correct sheaf. You should be thinking about perverse sheaf, and in that sense, you don't really have the sign. The sign is observed into the perversity. So let's repeat the conjecture. So instead of I want to do 2 implies 3. So let me make this conjecture. It's kind of hinted in a joint work with Liu and Max, but it's written explicitly in my paper with Donu. So if X has large Donu group, then the characteristic of FP, like any version, P on X. That's a conjecture. Well, we cannot prove this, and under some conditions, we will be adding some topological conditions. We will confirm this conjecture in some case. Any questions so far? Yes.
I keep saying that it's already perverse. You need effective characteristic sign.
Yeah, sure.
More general, you'll get more mild.
Yes, but yeah, it's true. But if we can prove this, then good enough. So okay, so the approach we are going to talk about today is through inductor. Okay, so first let me write down a result with Yongqiang Liu and Max. The theorem says so at least I'm assuming X is the compact Kähler manifold. Okay, so if I don't specify X is at least a compact Kähler manifold. So if the cotangent bundle of X, the holomorphic cotangent bundle of X is F, then the theorem, the consequences. So NF means it's like a limit of ample. If you're not familiar with the notion of NF, ample is always NF. And NF is kind of like the boundary of ample. Ample is open condition. NF is like taking closure. For rank 1, this is the case, but for higher rank, it has to be defined more in a more involved way. But the idea is being F is like the limit of being F. So if you have some positivity of the cotangent bundle, then you are done. And the proof is actually quite simple if you know the right machinery to use, which are, I mean, some kind of deep theorem. The first theorem, I mean, to get to this theorem, the first thing we need is Shafarevich index. Which says this: if F, okay, so here is more general. Let me say X, if X is complex manifold. And if F is bounded constructible or complex on X over some field, you can do C, you can also do other field. Then if you compute the Euler characteristic of F, it can has an intersection theoretic interpretation, which will be the characteristic cycle of F dot with the intersection with the zero section of the cotangent bundle, and the intersection happens in the cotangent bundle. So by this I mean the conormal bundle of X in X itself, and by that you mean we mean the zero section, right? Because it's only the zero cotangent vectors are like conormal to X. So this is the zero section of the cotangent holomorphic cotangent. And what is CCF? So this is called the characteristic cycle. F. Actually, for a constructible complex, the definition is quite technical, complicated and technical. If you like D modules, for D modules, there is a relatively clean definition, which I don't want to write down, but I can tell you. So instead, let's just do some examples. Let me first, how do they look like? They look like this. It's a linear combination. It's actually an integer combination of both conormal varieties. And these are also conic Lagrangian cycles. So here, Zi in X are irreducible some varieties. And if Zi is smooth, this is just the usual cotangent, conormal bundle over Zi, and which lives in the cotangent space of X. But if Zi is singular, it's defined by you take the smooth locus of Zi. For the smooth locus, you can define the cotangent bundle, conormal bundle, and then you take the closure in the cotangent bundle of X. So this could have singularities. So they look like the Kirk cycle of a constructible complex look like this. And let's do some examples. And it's kind of like the support of F, kind of the support with some atonicity. And also it also is sensitive to the singularity of F. Okay, let's do two examples. If Y in X is smooth, closed up manifold. Closed convex manifold. Then I can take the constant sheaf on Y, right? I can think of this as a controllable complex on X. And then if I do the Kähler cycle, I will get exactly the conormal variety of Y and X. But here with the sign, upward sign, the sign will be dimensional Y. So in particular, if Y equals X, I would have the Kähler cycle of the constant sheaf will be the zero section up to sign. The sign will be -1 dimensional X. So let's do another example where X equals C. Let's do a sheaf that's not a local system. And U is remove the origin. And so J is the inclusion map from U to X. I can do F. I can do Rj lower star of Cu. I could also take it to be J extension by 0 Cu. These two are like due to each other, so it doesn't matter which one you choose. The Kähler cycle will be same. The Kähler cycle of F will be in this case. Okay, again, because everything is one-dimensional, there will be like a -1 to the 1 here. So it will be actually negative cycles. It will be negative of Tx. So it's a zero section. Plus, but because I have minus sign here, I will also have minus sign here. It's T0. So T star of C, okay, T star of X equals T star of C is just a two-dimensional space. This is the base, this is the fiber. And so the Kähler cycle of this sheaf will just be the zero section plus the vertical section. I mean the vertical fiber over 0. So this is C. And you notice that there is always this annoying signs here and there. Again, the problem is because you are not really thinking about the right sheaf. You should think of the perverse sheaf. And if you do perverse sheaf, there will be no signs. So if this is a fact, if F equals P is a perverse sheaf, a complex manifold, then the Kähler cycle of F P, let's call it P. This P for perverse sheaves is effective. So that means all the Ni are negative integers. And you can see here the problem is Cy is not the perverse sheaf. You shift it by dimension Y, then become perverse. And once you shift by dimension Y, you get rid of this minus sign. This is the Kähler cycle. And here also F is not perverse. F you have to shift by 1 to make it perverse. And in that case, you get rid of the 2 minus sign, you have an effective sign. Okay, and Kähler's next theorem says once you can compute this Kähler cycle intersecting with the zero section, you get the intersection number will be the Euler cursive. So maybe first we notice that both these two cycles has is half of the dimension of the cotangent cycle. They both have the same dimension as X. So the intersection you do get a number. One minor issue is you may vary the cotangent bundle is not compact. So if you are taking intersection of two cycles in a non-compact space, how do you know it's well defined? Well, we know it's well defined because the support of the second cycle is compact. So for example, you can do the intersection theory. If you don't like the space being not compact, you can modify it any way you want. That wouldn't change the second factor. Compact it however you want. Replace the first cycle by its closure. However you want, you can imagine it wouldn't matter because you are changing things along infinity, and this cycle is supported at 0. So the intersection number wouldn't change. So this is well defined. Okay, so that's some facts about curve cycle and the Kashar's index theorem. And then we have another theorem of, in the projective case, and the ample and projective case, due to Fulton and lattice field. And in the Kähler and net case, is due to the Maillet. Here now. That's which does the following. If X is compact Kähler manifold, and E is an F vector bundle. X rank R. C is a conic cycle of dimension R. Then, so okay, so let me write down the. If I take C, I take the intersection number with the zero section. Of E, if I do the intersection in E again, it's well defined because the manifold is compact and the zero section is compact. Even though E is not compact, it's not a problem. If I do this intersection number, this is always positive. And here you notice that I require the dimension of C to be exactly complementary dimension of the zero section of E. So I get a number. It follows from basically the positivity of E. And in fact, I can prove easily this theorem in a special case. Just to give you some kind of conceptual explanation of this kind of positivity implies positive intersection. If E is globally generated, which is stronger than being that, then under the stronger assumption, we can prove this quite easily by, so this is left hand side. So left hand side of the inequality, so this part is equal to C times, this is globally generated, I can take a general section. Right, so a zero section and general section represent the same cycle, or topologically it's going to be the same cycle, or rationally with the same cycle. And then because now I have a general section, by like Martini theorem, it will intersect C transversely. Once you have a transversal intersection, the intersection number just counts the set theoretic intersection points. So we know this is just to see a very special case how this kind of theorem works. You know, once we have this two theorem, the proof of this all occurs, or this positivity becomes straightforward. Right, because now, let me say this is like the proof of this theorem. And W. It's just one line. If I compute the order of Perverse sheaf by Kashar's index theorem, I compute the intersection number of the characteristic cycle of P with the zero section. And I have also told you that for Perverse sheaf, the current cycle is effective. So the current cycle will look like this. in perverse tells me that ni are non-active. And the theorem of this 5 people together implies that, okay, just this part. Because I'm taking the 0 section of the conic cycle. That's what the whole thing is. So if we have something like cotangent bundle is left, then we're done. But again, the problem is cotangent left first is a geometric condition. And also a line bundle is ample or nap is something very easy to test. A cotangent bundle being nap is something that's actually pretty hard to show something is a vagabond is nap. So I mean it's a clean, nice result, but it's not a result that one can easily use to deduce something like the actual Singer-Hopf. But it does give us some cases. So for complicated manifolds, this is just the standard curvature condition calculation tells us that non-positive sectional curvature implies non-positive holomorphic bisectional curvature, and it implies that the cotangent bundle is left. And this was the condition 1. So you see, this is okay. So let me write it down corollary. So corollary is if any of the above condition holds, of the above the 3 condition holds, then we have this nice autocorrective property. Any conversion. Of course, if any of them hold by this implication, then let's have it. So basically, this gives, I think, it's quite like straightforward proof of why implies the autocorrective. So in the Kähler setting, this proves that. I mean, I read them. If you remember, 1 was the curvature condition, and 2 was the aspherical condition, 3 was the autocorrective condition, and 4 was the L2 vanishing condition. So basically, it gives the weaker conclusion that in the compact Kähler setting, Y implies 3. Okay. And then let me leave that term here for a moment. So then one may wonder if having large Donu group will imply the cotangent bundle is that. We actually write down this in my paper with Max, with Liu and Max. We actually conjecture something like this is true. So X has a large Donu group. Will this imply the cotangent bundle of X is natural? If something like this is true, then very good. We will be essentially done. If I only care about the autocorrective and in the Kähler setting. And the answer is no. Very sad. So it's a quite simple construction. It's written down by my student Yu. Okay, so let me not write down his full name so you don't confuse myself. For a generic double cover, of our belief variety. X. So the codangel bundle is not that. But X has a large number. Yeah, I think I need some words here. So for generic double ramified cover. So what do I mean by this? So you just take a belief variety, take a general ample variable hypersurface. Smooth, let's take a smooth one, and then you can take a double cover exactly ramified along that device. And then X, if you choose the things generic, then it gives you a counterexample of the simplification.
So I think the way you wrote it, X seems to be the abelian variety.
Yes. Cover X. Thanks. About abelian variety A. Okay. A is doesn't really matter. It's X. Right? Because X has a finite map to A. A has a large number group. That means X must have large number. And then it's actually so X. The replication locus is something X, and exactly like along that locus, you lose the netness. It's actually a simple observation, but it's kind of tricky. So this wouldn't work. So having large number group, you have to put something that's weaker here if you want to prove Singer-Hopf conjecture or the conjectures we made. It has to be something weaker. Any questions so far?
Well, that could be non-spherical, right?
Yes. So we are making, yeah, okay, that's a good point. We are making the assumption weaker. We are trying to include more things than just the spherical. Yes, actually, I have this in my notes, but I almost skipped it. Thank you for asking. But it's not the end of. I mean, if you only care about spherical, actually, I don't know. So here is the question: X is spherical. Does this imply codangel bundle is net? Then I don't know.
Actually, this is what we have in our table.
We actually had. I just checked before the talk. We had something like this. Yeah, perverse.
Why is this X is not net?
Why T star X is not net? You are saying here, why is not net? So I'm saying, so in X, you have a curve that maps to 1-to-1 to the ramification locus. Okay, so here I add the word ramified. So along that curve, you have like a rank 1 subsheaf of the codangel bundle. That's not.
You have a rank 1 subsheaf that's not.
Yes. It's not hard. I mean, if you read the paper, it's really like 1 page. It's simple, but it's not something I can just write down right now. Any other question? I'm for the end of my main part of my talk, so I think we will have like any. No, okay. If not, let me. So this is, I think, a nice approach, but just assuming X as large group wouldn't really give us really what we want. But I want to show you with some other assumptions or stronger assumptions, we can confirm the conjecture. So this is the theorem with Donu. So let's say X is the projective manifold. With a large number group. Okay, now I'm going to write down a very strong assumption. Suppose X, the Van group means cohomologically rigid, almost faithful. Very simple condition. The assumption is so strong that there are very limited examples that will satisfy it. But okay, let's assume this. So, right, so first, this is natural, right? We always assume X has not come otherwise. We don't expect anything. But now I put some very strong assumption on the. Then we can prove this. Very important.
Do you know other examples on Emerson lattice?
Sorry?
Do you know other examples on Emerson lattice?
No. No. Yes, I'm okay. So let me say so it's not, I mean, the statement itself is not interesting because all the examples we know has cotangent bundle being F. So for all examples past this strong condition, we could just do it directly using this. So all the examples we know has cotangent bundle being F. But I think the interesting part is if you look at all the previous results, all the assumptions involve some geometric condition, either curvature, netness, cotangent bundle, there is always something geometric. But here, this is purely topological. There is no yes.
Couldn't you do this type of, I mean, you could take a Hermitian symmetric space or something and make a covering, then it would satisfy that, but it would, yeah. Instead of a million variety, you take a Hermitian symmetric ball or something.
But ball quotient, for compact ball quotient, the cotangent bundle is always net.
No, then take a covering, like your student's example.
Sorry, I'm not understanding.
Then take a covering of that, a ramified cover of that,
Yes,
as in your student's example.
yes,
Then you said there, the cotangent bundle will not,
yes.
but it'll.
Yeah, I'm not trying to prove this using that.
That's what I'm saying. Still satisfy the hypothesis.
What?
Yeah, will that be still be cohomologically rigid?
Same.
Oh, okay. Let me think. So you have to take the cover use some tricky way, right? Because you take four times. So the ramified cover has a large ability part. Okay, yeah, it would be nice if we can demonstrate this one covers something that's not covered by that. Homologically rigid means the deformation space is should I put homologically? Oh yeah, almost faithful factor.
So can I interfere a bit? So I just checked the paper. We never really made that conjecture. Sorry, what you say?
Yes.
What we said is that a spherical should imply the universal coverage time, which is true for the Shafarevich is true. And then we said if the universal coverage time, then the cotangent should be net. But
yeah, this is the cover example. This is ramified cover. The universal coverage is time.
The second piece, but never to that thing down there. We
made a I'm sure we made a conjecture which is false because of this example.
No, the conjecture that's false is that universal coverage time implies netness of the potential part. That's the conjecture.
Yes, I mean, we made some conjecture like this. it's not important what exactly what we say, but the idea is here. And one particular conjecture, this provides a counterexample. Yeah, it's not important exactly what's. Okay, so let me just kind of give you outline how this the proof works, how to prove this, and this is really like the interesting part, which uses the Navier-Horst theory. Online. And you see why we need all this strong condition. So rho is rigid. There are two implications, or homologically rigid. The first implication is by ML, and Groshnik is actually a quite recent paper, where they prove that this implies that the associated local system is integral, or the representation is integral. So which means you can write down the matrices where the matrices are algebraic integers. And then by the work of Carlos, Elro underlies the matrices. And these two facts together, we imply that we can have a nice period map from X to period, so this period domain quotient like this. And we know that the period domain has negative equation. So at least on the horizontal section along the image of this map, it is negatively curved. And we also know that the map is finite because X has a large Donu group. And we know that the rho is faithful or almost faithful. Let's just say faithful. That's fine. Because it just cannot collapse any positive. If it collects any positive dimensional subvariety, that means the variation Hall structure restrict to that subvariety will be like constant family. That cannot happen. Okay. And now you see where we are getting. So from using this Navier-Horst theory, we actually have a map, finite map from X to something that's negatively curved. And this will allow us to kind of pull back the metric to X and push a metric. I mean, then we know X is kind of like negatively curved, except on some locus where it's ramified, but there it's like, so it's at least non-positively curved, something like this. And that's the idea. And let's make an argument in a special case. Let's assume that the image of X is smooth. In this case, we can have a simple proof of this theorem. So assume it's smooth, so let's actually call this Y. The image which is smooth, which is a submanifold of the period domain. Then what we can do is we can push forward Perverse sheaf. We start with Perverse sheaf on X. We can push forward to then this is a Perverse sheaf. Okay, it's a Perverse sheaf on the period domain, but because the image is in Y, so I can think of this as a Perverse sheaf on Y. Okay, or I can think of the finite map from X to Y. A finite map. Finite map reserve Perverse sheaves. The rapid forward of Perverse sheaf under finite map is also Perverse. Then we are basically done. Okay. So why are we done? Because the period domain is actively curved. And why the horizontal submanifold of the pure domain? So this tells me that y is negative curve. So in particular, the cotangent bundle is negative. I'm assuming y is smooth, so I can talk about this cotangent. Okay, now the order of P, the push forward doesn't change all characteristic. So the order characteristic of the push forward on y, and this is a negative by this result. Let me just quickly say that if the image is not smooth, and then we have to use some more refined intersection theoretic arguments. And which I mean the idea is here, which we actually follow from a paper, very inspiring paper by Johan. And Bruno. Which you somehow have to, because I mean there is also, it's not just about x and image of x. It's actually x is carrying a perverse sheaf. So you have to like argue quite carefully with the sum varieties of x, because there you have to really deal with the characteristic cycle.